Okay, here we go into two classic optimization problems. We'll start out with this one. The product of two positive numbers is 50. Okay, I stopped there. Right away, I actually have something I can translate, right? The product of two positive numbers, let's call those x and y, is 50, equals 50. So my secondary equation, the equation that has a number in it, just blasts out right there, right in front of us. Great. And the sum of twice the first, so let's just call x the first. So the sum of twice the first, that would be 2x, and the second plus y. So the sum would be adding them, and twice the first plus the second is a minimum. So I don't know, let's call that s for the sum. And we know that we're going to be minimizing this. It says find those two numbers. So essentially now we've got everything written out. That's the hard part. Here's our secondary equation. So I'll just call it secondary equation and primary equation. Let's do it. So the secondary equation, we're looking at it, doesn't really matter which one we solve for, though in this problem here, I think I'd rather plug in for y. So I'm going to solve this for y, only because we have 2 times something. It doesn't really technically matter what I solve for. So if I solve for y, I get y equals 50 over x. That's not so bad. So we have that. Now I take this bubble right here, and I plug it in for y. Nice. So now I've got 2x plus 50 over x, and that's equal to the sum, s. We'll just call it the sum. Now, from here, remember, it's all old school, right? We've made the translation. We have a function in terms of one variable. I'm just going to take a derivative now. So we can call that s of x, I guess. You don't have to, but it's the sum in terms of x. So I'll take the derivative and set it equal to 0. Now, before I do that, I notice that that would be a little bit more conducive to deriving if it was 50x to the negative 1. Just a little rewrite. And so the derivative is equal to 2, and then negative 50, negative 1 times 50, x to the minus 2. Okay, now we're going to set that equal to 0. When I do that, I'm going to want this to be in terms of just a positive exponent. So that's going to be minus 50 over x squared. All right, let's look for our critical numbers, or maybe just number. So I set that equal to 0, and now I'll solve it. So I subtract 2 from both sides, or add 50 over x squared. I guess I'll do that. So 2 equals 50 over x squared, looking for that critical number, and multiply both sides by x squared. Oh, it's sweet. The numbers are going to work out pretty nicely. Divide by 2, x squared equals 25, and then we get x equals plus or minus 5 as our critical numbers. Now, that's all they are, by the way. That's all we're doing is old school, finding a sign chart, and figuring out where hopefully we go from negative everywhere before and positive everywhere after. Now, negative 5 is not in the domain because we were asked for 2 positive numbers. Keep that in mind. So we're just looking at positive numbers. So the sign chart I'm looking at here is going to be from 0 all the way up. And you could figure out maybe what other endpoints are, but that typically is not going to be done, so I'm not going to go into that much advancement in these videos. So 5 is my critical number. Pick a number between 0 and 5. 1. So if I plug in 1 here into the derivative, you get 2 minus 50 over 1. That's negative. And then, and remember, this is for s prime, and this is for s that we're describing. So s is decreasing. The sum is decreasing everywhere up till 5. And then after 5, 22,000. 50 divided by 22,000 squared is a really small fraction. 2 minus a really small fraction is positive. So the sum is increasing everywhere thereafter. So your justification is, since the sum is decreasing everywhere from 0 to 5 and increasing everywhere thereafter, we will have our minimum sum when x equals 5. So I take x equals 5, and it says find the two numbers. I have the first number. To find the second number, I'm going to use this equation here, or that one, it doesn't matter. So y is equal to 50 over x, which is equal to 10. Those are our two numbers. That's it. Not bad, right? I think it's pretty cool. All right, on to the next one. Here we go. A rectangular refrigerator box with square bases has a surface area of 116 square feet. Let's stop there and let's draw a picture. Shall we? We shall. All right, so I've got a rectangular refrigerator box. Pardon me for the drawing. It's going to be a little bit different than you might be used to drawing out. But something like this, and let's pretend that the bases are squares. I'm trying my best here. All right, so you have something like that, and your bases are squares. Now, since the bases are squares, I'm going to call each of those edges x, right? Because they'd be the same length. They're square bases, and I'll call this side h. How do I know to put those variables there? Because those are the dimensions. Now we have a surface area of 116. That's going to be your secondary equation. So we'll write our surface area of this box. It has 6 sides. You have x squared on the top and bottom. So there's 2 of them. We're finding the surface area here. You're going to have 4 sides that are, and I'll kind of highlight it here, x by h. So each of these rectangles here, there's 4 of them, 1, 2, left side and back, 3, 4, would be xh. So that would be plus 4 of those x times h's, base times heights. And that will give you 116. Now that's going to be one heck of an equation to solve for, but we'll get there. It'll be okay, I promise. So this is your secondary equation. Well, what's our primary equation? It says find the dimensions of the box. That's great. Of the box that will have maximum, we're looking for maximum, volume. So that's our primary equation there. So what's volume? Volume would be equal to length times width times height, or x times h. X times x is x squared times h. Nice. Okay, we have a decision to make here. Do we solve the secondary equation for x, or do we solve it for h? They're both not looking good, but look in the volume equation. H will be easier to plug into because we don't have to square it like we do x. Therefore, solving for h is the way to go. So I'll solve this equation for h. I'll take that out over here. To do that, I'm going to take 2x squared and subtract it from both sides. So 116 minus 2x squared would be equal to 4xh. Let me erase a little bit of that, just to give us some more room. And that would be 4xh. All right, we're almost there. Then I'm going to divide both sides by 4x. That isolates h. And I'm not going to do much simplifying yet, because I don't really know what kind of format I need v to be in yet. But that is h. Okay, cool. I double check my algebra always to make sure it looks good, and it does. So I'm going to replace this for h in the primary equation. That'll give us v in terms of only x, which is our goal. So I've got x squared times all of this. 116 minus 2x squared all over 4x. And now from here, let's simplify this down. Please don't take a derivative yet. All right, write this as a polynomial. It'll actually be pretty nice. The x squared and the x here divide out, leaving you with an x. Now, what also happens is we can divide 4 into each of these terms, and I'm going to multiply x at the same time. So 4 goes into 116, I believe, 29 times x. So you have 29x. That's not bad. 2 goes into 4, well, it's going to be 1 over 2. So negative 1 over 2 x squared times x is negative 1 over 2 x cubed. Ah, that's a much nicer function. So we've gone through the hard part. No calculus has been taken or done yet. Now I'm going to take the derivative, right? All old school from this point. Isn't it funny that the calculus is the easy part? V prime is 29 minus 3/2 x squared. Ugh. Ugh. Look at that, 0 is going to be funky. So we're going to set that thing equal to 0. We're going to find our critical number. So I'm going to add 3/2 x squared to both sides. So it's going to be 29 equals 3/2 x squared. I'm going to multiply by 2/3 on both sides. That'll get rid of the 3/2, right? So multiply by 2/3 on both sides. And that leaves you with 58/3. 2 times 29 being 58 equals x squared. The 3/2 drop out. Now remember, we are dealing with the volume of a box here. So when I take a square root, normally I would do plus or minus. We only have to do plus square root because of the domain of this real world problem. And please don't rationalize. Just leave your answer as x equals root 58/3. All right, let's look at our sign chart. We started at 0 because, again, x cannot be anything less than 0 here. They're dimensions of a box. Okay, so I've got root 58/3. Now, whatever that is, I know it's more than 1. So when I'm looking at the volume and how it behaves in v prime, I know I'm going to be plugging in a number that is less than this. So again, 1. If I plug 1 into the derivative, I get 29 minus 3/2, which is positive. And that's a good start because we want to go from positive to negative for maximum. Something greater than root 58/3. How about, I don't know, any number greater, 100. 29 minus 3/2 times 100 squared, that's going to be a big number, and 29 minus it will make it negative. So we've got a maximum at x equals root 58/3. The justification is since v prime is positive everywhere before this number and negative everywhere thereafter. Okay, so from here, all we do is we take this value. We want to find the dimensions. Well, we have 2 of the dimensions now. 1 and 2, we want to find the height. How do we do that? We plug it into here. And again, please don't simplify, right, at all. So x is equal to that. Your dimensions then would be root 58 thirds. And yes, the numbers are this nasty. By root 58 thirds. And watch this. I'm just going to plug it into h. So that's going to be 116 minus 2. Now, this right here is going to be just plug it in. If you have a calculator, you can do it out. I'm going to save time and just show you the plug-in and leave it at that. I know that'll annoy some of you. It's just not worth the time in the video to watch me plug things into a calculator, though. That is h. Those are your 3 dimensions. That's it. I will see you in the next video.